In this final screencast for Chapter 11, we discuss vertices of quadratic functions, and we pull together all of the graphical information we've discussed from the previous screencasts. We know that a quadratic function will have exactly one vertex, one turning point, but how do we locate it without looking at a graph? As with horizontal intercepts, if you take higher level algebra and calculus courses, you will learn multiple approaches for determining the vertex of a quadratic function. Here we state a basic fact concerning the location of vertices. The location of the vertex of a parabola. If a quadratic function is given by the equation f at x equaling ax squared plus bx plus c, in other words, the standard form of a quadratic function, then the vertex of the parabola graphed by the function is located at this point. Notice that this point is an input-output pair for the function f. So, in other words, if I draw a small graph here in the margin, so here's a parabola. The vertex of this parabola is down here. You can see it right around that point. What we're saying in this fact is that we have a formula for the coordinates of the vertex. The first coordinate of the vertex is given by the formula minus b over 2a, where a and b are the numbers in the standard form of the equation. So this formula gives you the coordinate, the first coordinate of the vertex. To find the second coordinate of the vertex, or the so-called y value, you take this number, which remember would be an input. It would be an input for your function. The y value would be the output. So to find the y value, or the output, you will take your function and you will substitute this number into it. So the input-output pair, input-output, will give you the coordinates of the vertex. This fact will be useful in the following two examples. So in this next example, we're going to pull together all of the big ideas we've talked about in graphing quadratic functions. Example 11.7. Consider the quadratic function that's given by the equation g at x equaling x squared minus 4x plus 3. You can tell that this is a quadratic function. It's written in standard form. A is 1, b is negative 4, and c is 3. All right, let's look at part A. Does the parabola graphed by this function open up or down? Well, we've learned that we can tell by looking at the value of a. Since a is 1, that is a positive number. That tells us that the parabola opens upward. Now let's look at part B. Determine the location of the vertex. Well, that is where our fact that we've just learned will be helpful. To determine the first coordinate of the vertex, we use this formula. So let's try it out here. The x value is minus b over 2a. B is negative 4, so it's minus a negative 4 all over 2 times a. A is 1, so we have 2 times 1. Now we simplify. The numerator is 4, the denominator is 2, and so we arrive at 2. So that tells us that if we were to graph this vertex, the first coordinate of the vertex is 2. So this vertex lies somewhere along this line. Or, put another way, what we know is that the vertex is at 2 comma something, and we have to work out the second coordinate. But remember, the vertex is a point on the graph, which means it's an input-output pair for the function. The 2 is input. To find the second number, we look for the output. So we have to take our 2 and substitute it into the function. So I put 2 into the g function, and g will square the 2, subtract 4 times 2, and add 3. So we have 4 minus 8 plus 3. That's a negative 4 plus 3, which is a negative 1. So that's the output. So that is the number that sits right here. So that is the location of the turning point, or the vertex. Now let's look at part C. Determine the horizontal intercepts of the parabola. We discussed this in the previous screencast. So if you recall, we start by factoring our function. So we have g at x equaling x squared minus 4x plus 3, and we want to write this in factored form. The factored form for this function is x minus 3, x minus 1. You can check. Negative 3 times negative 1 gives a positive 3. When you add negative 3 and negative 1, you get a negative 4. Okay, now to find horizontal intercepts, we set our output, that would be g at x, equal to 0, and we have to find x. So we set x minus 3 times x minus 1 equal to 0. And we use the zero product property. And from here we know that either x minus 3 must be 0 or x minus 1 must be 0. One of those must be true. So from here we know that x must equal 3 or x must equal 1. So there are two values of x that cause the output to be 0, and this tells us that there are two x-intercepts. So there are two x-intercepts at x equaling 1 and x equaling 3. Now let's look at part D. Determine the vertical intercept of the parabola. Well, to find a vertical intercept, we set our input equal to 0. So in this case, that means we're going to set x equal to 0 because that's our input variable, and we find our output. So if I substitute 0 into the function, we get 0 squared minus 4 times 0 plus 3. When you simplify, you get 3. So the vertical intercept is 3. Now let's look at part E. Let's sketch a graph of the parabola using only your answers in parts A through D. Alright, so in part E, we're putting all of the information we've gathered together to sketch one graph. Let's start by drawing some axes. We have an axis that represents our input x and an axis that represents our output g at x. And we can put in some tick marks. Let's declare that to be 2, and that can be 4. So there's 2, there's 4. This can be -2 right here, -4, and we can have 1, 2, 3, and 4. So there's 2 and there's 4. Okay, part A from this example told us that the parabola opens upward, so we should expect that. In part B, we determined the vertex of this parabola. It is at the point 2, -1, which would be right about here. In part C, we determined the horizontal intercepts of the parabola, or the x-intercepts in this case. They are located at x equals 1 and x equals 3. So here and here. In part D, we determined the vertical intercept of this parabola, and that is at 3. So the graph crosses the vertical axis at 3. So if we connect our points with a smooth curve, we arrive at a graph that looks like this, and you can see that it is an upward opening parabola. For this final screencast for Chapter 11, we go back to an example that we talked about at the beginning of the chapter on water consumption. Recall that the function describing annual water consumption for a town was given by the equation W equals -128,000 t squared plus 3,200,000 t plus 125,800,000. W described the annual consumption for the town in gallons, and T represented time in years since the year 2000. In the earlier example, we drew a graph of this function, or a partial graph of it. We can reconstruct it here quickly. So here was T, time, and W, and the graph generally looked like this. Let's look at part A. Does the parabola graphed by this function open up or down? Well, I hope we all agree now that the function describing the town's water consumption is quadratic. You can see it has the form ax squared plus bx plus c. A for this function is a negative number, which would imply that the graph of this function is a parabola that opens down. And in fact, that's what we saw. When we graphed this function earlier, it appears to be a downward opening arch. So here A is equal to minus 128,000, which is negative. So in this case, the parabola should open downward. Let's look at part B. In what year is the total water consumption for the town predicted to peak? Use the formula for the vertex discussed on the previous page. Well, let's look at this graph that we've drawn here. Peak consumption would occur right here. That would tell us the point in time at which consumption was the highest. And right at this value, that would be the highest level of consumption for the town. So right there, that is peak consumption. And notice that peak consumption is represented by the vertex. Our goal is to find out in what year this peak occurs. So really what we want to know is what time. What is the value of t for which this peak occurs? But we can use our formula. We know that the vertex occurs at minus b over 2a. That would give us the horizontal component, or the first coordinate of the vertex. So let's use that here. So the time is minus b over 2a. For this quadratic function, b up above is 3,200,000 and a is negative 128,000. So we substitute those in. So minus 3,200,000 divided by 2 times a. And then we simplify. And when we simplify, we arrive at 12.5. So that tells us that this mystery number here is 12.5, and t represents years since the year 2000. So 12.5 years after the year 2000 is when this town is predicted to see its peak consumption of water. This would be in the year 2012, somewhere midway through the year 2012.